Hello friends, welcome you all to the 44th lecture on function analysis and its applications. In this lecture, we will discuss the adjoint of an operator on a Hilbert space. The content of today's lecture is the adjoint of an operator on a Hilbert space. Let H be a Hilbert space. If T is a continuous linear transformation from H into H, then T is called an operator on H. The set of all operators on H is denoted by BH. Let T be the operator on H, then the operator T on H gives rise to a unique operator T star on H star, such that T star f x equal to f of Tx for all f belonging to H star and x belonging to H. The operator T star on H star is called the conjugate of the operator T on H. The mapping T to T star of BH into BH star is an isometric isomorphism of BH into BH star, which reverses the products and preserves the identity transformation, as discussed in previous lecture. Theorem: let T be an operator on Hilbert space H, then there exists a unique operator T star on H such that inner product of Tx and y equal to inner product of x and T star y for all x, y belonging to H. The operator T star is called the adjoint operator T. Proof: existence of adjoint operator. We prove that if T is an operator on H, that is T such that H to H, then there exists a mapping T star on H into itself, that is T star such that H to H, such that inner product of T x y equal to inner product of x T star y for all x y belonging to H. Let y is the element of H and fy its corresponding functional in H star, that is fy belonging to H star. Let us define T star on H star into H star, that is T star such that H star to H star by T star fy equal to fz. Okay. Under the natural correspondence between H and H star, let Z belonging to H corresponding to fz belonging to H star. Thus, starting with vector y belonging to H, we arrive at the vector Z belonging to H in the following manner. Y is the element of H, so y to fy and fy to T star fy and T star fy equal to fz. This to Z. Okay. There is 3 mapping where T star such that H star to H star and y to fy and z to fz are H to H star. Okay, here y in H, fy belonging to H star. Here also z belonging to H and fz belonging to H star. So y to fy and z to fz are on H to H star under the natural correspondence. The product of the above 3 mappings exists and denoted by T star. Then T star is a mapping on H into H such that T star y is equal to Z. Okay. We define this T star to be the adjoint of T. Note that if we identify H and H star by the natural correspondence Y to Fy, then conjugate of T and adjoint of T are one and same. After establishing the existence of T star, we prove equation 1. For X belonging to H, from the definition of the conjugate T star of an operator T as T star Fyx is equal to Fytx. Okay, as per the definition of conjugate T star by this. Okay, so we have T star Fyx is equal to Fytx, and this by rigid representation theorem we can write inner product of Tx and Y. Since T star is defined on H star, we have T star Fyx equal to Fzx, because here T star defined on H star. So T star Fy is equal to Fz, this one. So we can write T star Fyx is equal to Fzx. Again, by rigid representation theorem, this can be written as inner product of X and Z. Z is T star Y, this one. So inner product of Xz equal to inner product of X T star Y. We put here Z is equal to T star Y. Thus from equation 2 and 3, here in equation 2 T star Fyx is equal to inner product of Tx Y, and here same T star Fyx equal to inner product of X T star Y. So from 2 and 3 we have inner product of T, X and Y equal to inner product of X and T star Y for all xy belonging to H. Hence proved. This representation can also be defined as inner product of T star xy equal to inner product of X and Ty. How to say it? Let us prove it. In this way, we see that there exists a mapping T star of H into itself which satisfies the property 1. Hence, the relation inner product of T x y equal to X T star Y can be written in the equivalent form inner product of T star x y is equal to inner product of X T Y. We see this form inner product of T star x y equal to conjugate complex of the inner product of Y and T star x as per the definition of inner product. Here we change the position of Y and T star x, that is conjugate complex of the inner product of Y and T star x. Okay, so as per this definition, inner product of X T star Y is inner product of T x Y. So this can be written as conjugate complex of the inner product of T y x. Okay, here T x y, then here X T star Y, here T star x and Y, that is this can be written as T y x. Okay, as per this. Again we change the position of X and Ty, so that is again conjugate complex. So here double conjugate complex of the inner product of X and Ty. So we have inner product of X and Ty. So inner product of T star x y can be written as inner product of the X and Ty also. Hence we have inner product of T star xy is equal to inner product of X and Ty. Now we shall show that this mapping T star on H into itself is an operator on H For this, we are to show that the mapping T star is linear and continuous. So now we prove in another theorem T star as a linear and continuous. Let H be the given Hilbert space and T star be the adjoint of the operator T. Then the T star is bounded linear transformation and determines T star uniquely. Okay. So here T star is linear and continuous, that is T star is linear and bounded. Let us prove T star is linear. Let y1, y2 belonging to H and alpha beta be any scalars. Then for x belonging to H, we have inner product of x T star alpha y1 plus beta y2 equal to inner product of Tx and alpha y1 plus beta y2 as per the equation 1. Okay. This. So by the property of inner product, this can be written as inner product of Tx alpha y1 plus inner product of Tx and beta y2. So by conjugate linearity property of inner product, this can be written as alpha bar inner product of Tx y1 and this is also plus beta bar inner product of Tx y2. Again by the property 1, this can be written as alpha bar into inner product of x and T star y1 plus beta bar into inner product of x T star y2. Okay, by property 1. And by the conjugate linearity property of inner product, this can be written as inner product of x alpha T star y1 plus inner product of x beta into T star y2. Okay. So here alpha double bar and here beta double bar. We know that alpha double bar, that is alpha, and beta double bar, that is beta. So we have this. Okay. So again using the triangle property of inner product, this can be written as inner product of x and alpha T star y1 plus beta T star y2. Thus we have T star alpha y1 plus beta y2 is equal to alpha T star y1 plus beta T star y2 for all x belonging to H. Because we know that inner product of xy equal to inner product of xz, then y is equal to z. So using this property, here we have this one equal to this. Okay. Here it will be inner product. Okay. Thus the mapping T star is linear. Now we prove T star is bounded. For any vector y in H, we have square of the norm of T star y equal to inner product of T star y and T star y. Okay, because we know that norm of x square equal to inner product of x and x. So using this property, we can write this one as this. So again, as per the property 1, this can be written as the inner product of T star y and y. This can be written as the modulus of the inner product of T star y and y, because this is norm and this is greater or equal to 0. Norm greater or equal to 0. So this can be written as positive, this one. Okay. So by Schwarz inequality, this can be written as norm of T star y into norm of y. Okay. So T star y can be written as norm of T into norm of T star y because T is bounded linear transformation. Okay. Since T is bounded linear transformation, so this can be written as this less or equal to norm of T into norm of T star y into norm of y. Okay, because norm of Tx less or equal to norm T into norm x. Okay, so here this norm T star y, here square of the norm T star y. So we can write, thus we have T star y less or equal to norm T norm y. Okay, so this one is cancelled out. Okay, norm T as scalar, that is positive constant k. So we can write norm of T star y less or equal to k norm y. This shows that T star is bounded. T star is bounded, so it is continuous. Uniqueness of the adjoint operator. Now we shall show that if there exists any mapping T dash on H into itself such that inner product of T x y equal to inner product of x T dash y. Okay, because here mapping T dash of H into itself. So we can write this. Then we must have T dash is equal to T star. We have inner product of T x y equal to inner product of x T dash y. Okay, and also inner product of T x y equal to inner product of x T star y. Okay, so this implies that inner product of x T dash y equal to inner product of x T star y. So again, using the property, if inner product of xz is equal to inner product of xy, then z is equal to y. So here inner product of x T dash y equal to inner product of x T star y. It means T dash y is equal to T star y. Hence T dash is equal to T star. This proves the uniqueness of the adjoint operator. Noting point, using equation 1, we note that 0 operator O and the identity operator I are adjoint operators, as seen below. For x, y belonging to H, we get first inner product of x O star y. Okay, as per the property 1. Property 1 is x T star y equal to Tx y. So using this property, we can write inner product of x O star y equal to inner product of Ox and y. So this is a Ox, O is 0 operator, that is this is 0 vector. Okay, so this one is inner product of 0 y, that is 0, and 0 can be written as the inner product of x and 0 vector. Okay, and again this can be written as inner product of the x and 0 operator of y. So again using this property, if inner product of xz is equal to inner product of xy, then z is equal to y. So by that property, here O star y equal to OI. That is, O star is equal to O. Okay. So from the uniqueness of the adjoint, we get O star is equal to O. Similarly, for identity operator, inner product of X and I star Y can be written as by this property. Inner product of Ix and Y, I is the identity operator, so it can be written as inner product of X and Y. Again, using the property of identity operator, this inner product can be written as the inner product of X and identity of Y. Again, from the uniqueness of the adjoint operator, I star Y is equal to IY, that is by uniqueness of the adjoint operator, I star is equal to I. In this lecture, we have discussed the adjoint of an operator on a Hilbert space. These are the references which have been used in this lecture. Function analysis, Dover publications written by George Beckman and Lawrence Naresi. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Water-Rudin. Thank you.